Hello everyone, this is another video for the Intro to Signal Analysis course. In this video we'll work through 4 examples that illustrate the different types of effects we see when sampling sinusoidal signals. I assume you're familiar with the basic concept of sampling, and if you're not, you could watch the earlier video on this topic. So let's get started with these examples. The examples that we'll consider today are for sampling this particular signal. X of t is 6 cosine 2 pi times 2t plus pi over 4. So that's the sinusoid that we're going to be sampling, and we represent the sampling process by this ideal box called a C to D, or continuous to discrete converter. So that takes x of t and converts it to a series of samples x of n, and then we'll consider what happens when we recreate a continuous time signal from that set of samples by running them through a D to C converter that undoes the sampling. And then the output is XR of t, the reconstructed signal. Now we know that the spectrum of this signal, x of t, looks like this. It has spikes here at -2 and +2, since the frequency is 2 hertz. And the amplitudes of these are 3 e to the j pi over 4 at +2 and 3 e to the minus j pi over 4 at -2. And we're going to consider 4 different cases. So we're always going to be sampling the same sinusoid, but we're going to do so with 4 different sampling frequencies: 5 hertz, 3 hertz, 2 hertz, and 1 hertz. And for each of these cases, what we're going to do is we're going to sketch the spectrum associated with the sampled signal and the spectrum associated with the reconstructed signal. And we're also going to write an equation for x of n and an equation for xr of t. So let's get going with the fs equal 5 hertz case. Okay, so the first thing to ask ourselves when we start a sampling problem is, do we expect to see aliasing? Well, remember that the signal that we're sampling has a frequency of 2 hertz, and we're sampling it at a rate of 5 hertz. And so since fs is greater than twice the highest frequency, meaning greater than 2 times 2 in this case, we don't expect aliasing. So the answer to this question is no. All right, so as we go through and solve this problem, we don't expect to see any aliasing. Okay, so the first thing we do, we've got to sketch the spectrum of the sampled signal. Now, we can start by just sketching. The first thing we do, we sketch, well, what is the spectrum of the signal that we're sampling? And we know that that looks like this. It has frequency components at plus and minus 2. And this is just recopying what we had on the previous page. So that's 3 e to the minus j pi over 4, and that's 3 e to the j plus pi over 4. Okay, so that's what we start off with. But remember, what happens when we do sampling is that we create copies of this particular spectrum along this axis, and those copies are located at integer multiples of the sample frequency. So I'm going to sketch the copy that goes at the sample frequency, so that's 5 hertz in this case, so that's 5, and so we get a copy of this spectrum located centered around 5. I'm going to draw that copy in blue. Okay, so if I center the spectrum around 5, then I get a component 2 to the left of 5, which is at 3, and 2 to the right of 5. Now I'm going to have to erase here and lengthen my axis a little bit so I can get it all on here. Okay, so 2 to the right of 5 is 7. Okay, and remember, this is the f-axis. Okay, that's the frequency axis there. Okay, so I get those, and they have, I can complete labeling here, 3 e to the minus j pi over 4, 3 e to the plus j pi over 4. And again, this is just an exact copy This is an exact copy of what's right here. We also have a copy at -5, and so I'll draw that on here. The copy at -5 I'm going to draw in red, and we get something at -7 and then -3. And they have the heights 3e to the minus j pi over 4, 3e to the plus j pi over 4. Okay, and these copies actually keep going on. If we drew a longer axis, we would draw more of those copies on out to infinity in both directions. Okay, so we've got the copies there. We've completely drawn our spectrum of the sampled signal. Now we could rescale the axis. We talked about axis normalization in a previous video, and if we're going to do that, we define an axis f hat, where f hat is just f divided by f sub s. So we could redraw the same spectrum just on this axis, where we're going to divide all of the axis points by f sub s, which is 5 in this case. So this shows up at 2/5 minus 2/5. And then we have our copy in blue, and that shows up at 3/5 and 7/5. It's centered around 5/5, which is 1. And then the copy to the left is centered around -1, and its little spikes are at -7/5 and -3/5. And I won't bother labeling the heights of these spectra, but they all should look like they're equal height. Okay, so this, having the axis labeled this way, is what helps us to get an equation for x of n. So our equation for x of n is just simply going to be x of n. It's the cosine associated with this, this frequency, these two frequencies here. So that's cosine of, well, again, we have to remember what the height is here. So these heights are 3, which means the cosine has an amplitude of 6. 6 cosine 2 pi times 2/5 n plus pi over 4. Okay, and it's plus pi over 4 because we have e to the j pi over 4 is the phase associated with this, the spike on the right. We have the 2 pi in here because this is all we're putting in radian frequency here. So this is really, this frequency here is omega hat, which is 2 pi f hat. Okay, so that's our equation for x of n. So x of n is 6 cosine 2 pi times 2/5 n plus pi over 4. All right. So now the question is, well, what signal would get reconstructed from this set of samples? And remember from our previous video that the signal that gets reconstructed, when we run through the D to C converter, it just picks out the spectrum between minus fs over 2 and plus fs over 2. So this is fs over 2, which in this case is 2.5, and this is minus fs over 2, or minus 2.5. So we just pick out the spectrum that lies in here, and that's what we get for the spectrum of xr of t, the reconstructed signal. And so I'll sketch this down here at the bottom. The spectrum of xr of t is just going to look like, it's just going to pick out these two things at -2 and +2, and they have the complex amplitudes 3e to the j pi over 4 and 3e to the minus j pi over 4. And we can easily see that that corresponds to the spectrum of a cosine, which is xr of t, 6 cosine 2 pi times 2t plus pi over 4. Now we notice that this is exactly the same as x of t, which is the signal we sampled. We expected that. Why? Because we didn't expect aliasing. So we expected that we could take samples of this particular cosine and then reconstruct the cosine from its samples without any errors. And that's what we did here. So xr of t is this 6 cosine 2 pi 2t plus pi over 4, which is what we started with. Okay, so what did we do here? We first sketched the spectrum of the sampled signal. We redrew that spectrum just to draw it on our normalized frequency axis. And the normalized frequency axis, that's what gets us the frequency of our discrete time signal, our set of samples x of n. Okay. And then we reconstructed the signal, and we viewed the reconstruction process as just picking out this part of the spectrum that lies between minus fs over 2 and plus fs over 2. And that gets us this spectrum back, and that corresponds to the spectrum of the sinusoid that is exactly the same sinusoid that we started off with. Okay, so that was the first case. In the first case, we had absolutely no aliasing, and so this was a pretty straightforward process. So now we're going to go to the next case and see what happens there. So the next case, we're going to sample this same sinusoid at a frequency of 3 Hertz. So in this case, do we expect aliasing? Well, yes, we do expect aliasing. Yes. Why? Because Fs is equal to 3, which is less than 2 times 2, which is less than 4, right? It's less than twice the highest frequency in the signal. So we expect aliasing of the signal. So we don't expect to be able to reconstruct the same signal at the output of this process as goes into the process. All right, so let's go ahead and work through what's going on here with this by, again, just drawing the spectrum of the sampled signal first. Okay, so again, we start by just drawing the spectrum of the signal that we're starting off with. Okay, and so that has the spikes at plus and minus 2. Okay, and this is 3e to the j pi over 4, 3e to the minus j pi over 4. Okay, well, the process of sampling, what happens when we go through the process of sampling is we make copies of the spectrum. So again, I'm going to draw these copies in color. And the first copy is showing up to the right. Well, it's centered around plus 3. Okay, so if I pick up and draw a copy of this thing, now I just move it so the center of it is around plus 3. Well, then I'm going to get something 2 to the left. So I'm going to get that, and I'm going to get something over here at 5. Okay, and this has a height of 3e to the minus j pi over 4, and this is 3e to the plus j pi over 4. So that's the copy centered around 3. Okay, and that's at 1. All right, now I'm going to draw the copy to the left of the origin, and that copy is going to occur at minus 3. And so it's going to have one of its spikes at minus 5 and one of its spikes at minus 1. And so I'm just going to label these 3e to the minus j pi over 4, 3e to the plus j pi over 4. Okay, and again, we would get more copies. We could keep drawing them on out, but we're not going to do that here. Okay, so now the question is, well, what are we getting here? Okay, well, first let's go ahead and think about what happens when we normalize the frequency axis. Well, first of all, let's notice one thing. Now, when we've drawn these copies, now the copies actually show up inside of the original signal. And remember, the only part we end up with a spectrum here that's periodic, and the only part that's unique is really lies between minus fs over 2 and plus fs over 2. So the part that's unique lies here, and everything else is just repeated outside that. So that's minus fs over 2 and plus fs over 2, which in this case is 1.5. Okay? Okay, so now we could redraw this in terms of f hat. That would just end up, we'd relabel these axes, and that's straightforward to do. So if we sketch this in terms of f hat, then what are we going to have? Well, we're going to have that right there. I got to switch colors more here. And that right there. And those are going to be located at, we're just dividing the axis. F hat is f over fs. So we just divide by 3, divide everything by 3. So this is at 1/3, and this is at minus 1/3. And then we have copies of this thing outside of there. This is at 2/3. This is at 5/3. We have things over here at minus 2/3, minus 5/3, and again, we have more and more copies that we'd have to continue drawing, but all we really care about is what lives between here and here. Okay, so the frequency here of these two components, which is really going to be the frequency of the sampled sine wave, is 1/3. F hat is equal to 1/3, so we can now write an equation for x of n. X of n now is going to be 6. It's 6 because the amplitude of these is 3. 6 cosine of 2 pi times now 1/3 n. And now the question is, well, what is the sign of this phase that gets added? Well, what is the sign here? It's minus pi over 4. So this is minus pi over 4. Okay, because we always pick the phase of the cosine is going to be the phase of whatever term is to the right of the origin, right? Okay, so that's our equation for x of n, 6 cosine 2 pi times 1/3. So that's one. Let me erase this and make this a little clearer. 2 pi times 1/3 n minus pi over 4. All right, that's what x of n is equal to. Now we're asked, well, what is the spectrum of the reconstructed signal? Well, the spectrum of the reconstructed signal, we just pick out whatever this copy is between minus fs over 2 and plus fs over 2. And when we do that, here's what we get. We're picking that out. And this is labeled an F now. It's not the normalized frequency axis. And so those components are at minus 1 and plus 1. And that has a complex amplitude of 3e to the minus j pi over 4. Let's see if I can sketch that a little bit better. 3e to the minus j, excuse me, pi over 4. And 3e to the plus j pi over 4. So this, we can just read off the spectrum here. We're going to say x of t is 6 cosine 2 pi times 1t minus pi over 4. Okay, so now was this equal to the signal that we put in? No, it's not. it actually has a different frequency. It has a lower frequency than the signal we put in. The signal we put in had a frequency of 2 hertz, and this has a frequency of 1 hertz. And the other thing we noticed the sign change here on the phase part of this. And this corresponds to what they term in the DSP first book as folding. So not only has the frequency changed, but the phase has changed as well. Okay, and that's because the copies here moved inside. Because the sample frequency was lower, the copies actually showed up inside of where the original signal was. And so our higher frequency signal now is aliased down into a lower frequency signal with a different phase. So this was case 2, and in this case we expected aliasing, and we could easily, by doing these sketches of the aliased signal spectrum, we were able to determine what signal we would get out of this reconstruction. Okay, so that was case 2. Now we're going to lower the sample frequency some more and see what happens in the next case. Okay, the next case that we're going to consider is the case where the sampling frequency is equal to 2 hertz. Now, on this one, I'm going to challenge you to pause the video and go ahead and do the sketches of the sampled signal and the reconstructed signal for yourself, and then we can compare notes when you unpause the video. Okay, hopefully you worked through it on your own and figured out what happens with this problem. So let's take a look. First of all, did you expect that aliasing would occur? Hopefully you said yes, because the sample frequency 2 hertz happens to be the same frequency as the signal, which is also 2 hertz. So certainly we expect aliasing because we're not sampling at a rate twice the maximum frequency in the signal. If we go ahead and sketch all of our copies of the spectrum, which is what happens when we sample a signal, well, something very interesting happens here. So I've sketched the original, that's these black lines, and then I've sketched a copy at -2 and a copy at +2, okay? And we notice something very strange here. The copy, both at -2 and +2, sticks a line right at the origin. So these lines would technically be right on top of one another, but it's a little hard to see that, so I've drawn them next to each other. And so that's what we get here. Now, we should get an exact replica of that at every single frequency here, but in order to see that, we'd have to draw another copy up at 4, and that would put another line here, and another copy at -4, which would put another line here. So that we're just going to get single lines reproduced. But we have to add these together, so we have to add 3e to the j pi over 4 to 3e to the minus j pi over 4. And I did that on this graph below. I'm now sketching the overall spectrum that we get on this normalized scale for f hat is f over fs. For that case, we get a line here at 0, and it has a height of 6 cosine pi over 4, because that's the addition of these two things here. I get a line here at 1, which, remember, the sample frequency in this normalized scale moves to 1, and then this is twice the sample frequency, etc. And all of these lines have the same height of 6 cosine pi over 4. Okay. So that's what we get, and so what do we get for our signal x of n? Well, our signal x of n just becomes x of n is 6 cosine pi over 4. This is a constant. This is a constant, right? A constant signal, a DC signal, has 0 frequency, okay, and it just stays level, and it stays level in this case at 6 cosine pi over 4. Now, does this make sense? We'd have to think back at how we're sampling this signal. I think it does make sense. Remember, this is a cosine. The signal we're sampling is a cosine, 6 cosine 2 pi 2t plus pi over 4. Let's sketch this out on the next page. So this is still case 3. X of t was 6 cosine 2 pi 2t plus pi over 4. So we could have sketched that signal as a function of time. Here's 0, and this is 0.5. The period here, right, t0 is equal to 1 over 2, 1/2, right, because f0 is 2. So it should repeat every half a second. And the plus pi over 4 here, we've got actually a small shift of this signal. So it's a cosine, it's shifted to the left here by minus 0.0625. So the peak is here, and then it's going to go down and come back up here. And it's going to repeat every half second, right? So the total period here, something looks off. I don't think I've sketched that correctly, so let's start this over. So let me start by, I think it'll be easier if I just draw a sine wave. Okay, and we know that between here and here is 0.5 seconds. And that the peak here occurs at minus 0.0625 seconds. And we can easily find that because remember the peak, we can solve for t1 is equal to minus phi1 over omega naught, which in this case is minus pi over 4 over omega naught, which is 2 pi times 2. And I believe that comes out to minus 0.602. Whoops. 0.6. I'll get this right one of these days. Minus 0.0625 seconds. Okay, so that's a half second. Now we're trying to think about, well, what was our sample rate in this case? Our sample rate was 2 hertz. So we've got a sample at 0. So we're sampling it at 0, which is somewhere here. Sampling it at 0, and then when are we sampling it again? Well, we're sampling it again half a second later here. And then we sample it half a second later, which again is 1 full period. So we should get a constant. And the constant that we get, this will be whatever the value is at 0, which is 6 cosine 0 plus pi over 4. So it's 6 cosine pi over 4, which is exactly what we got out of our spectral picture. Okay, so we should have been easily able to see from the start that sampling this cosine at a rate of 2 hertz is just going to get us a constant because we're sampling once per period. Okay, if we go back now to the previous, we can look at the rest of the problem. So if we reconstruct this signal from its samples, again, we pull out everything between plus and minus fs over 2. Plus and minus fs over 2, well, fs is 2 hertz, so, whoops, gotta get the right color here. We're just pulling out everything in there. That's fs over 2, that's minus fs over 2. And the result is this signal down here, which is, again, just a constant. So we clearly had aliasing. We've sampled a sinusoidal signal at a frequency of 2 hertz, and we have gotten a constant signal back out. Okay, so we just have one more case to consider, and that's case 4. Okay, so with case 4, we're sampling at a rate of 1 hertz, and so we've lowered the sample rate even more. So the answer to the question, do we expect aliasing? Well, yes, clearly we expect aliasing. These other signals have been aliased, so we would certainly expect this one, that to be the case. So again, take a break, turn off the video for a few minutes, do your own sketches, and then we'll compare notes. Okay, hopefully you did this last case on your own and figured out what's going on. So in this case, we were sampling at a rate of 1 hertz. We certainly expect aliasing again, and so now we just go ahead and draw all the copies. And here we've got to draw some more copies even than we did before. So I've drawn the copy around 0, that's the black. I drew the copy around 1 hertz, that's the blue lines here. I drew the copy around 2 hertz, that's the orange lines here. And then I also drew a copy around minus 1, that's the red, and a copy around minus 2, and that's the purple lines here. And we see again that we're getting lines that are going to add up right next to one another. So, and if we drew all of the copies that go even farther out, we would get, at each point, we'd get 2 lines next to one another. So we get 6 cosine pi over 4 again. Now, does this make sense? Well, if we go back, what have we done? We're sampling the same sinusoid now at a rate of 1 hertz instead of 2. So that's 1 sample every 1 second. Well, here's the signal we're sampling. We go back to our case 3 drawing. And now we're just going to sample it instead of sampling it every half second, we sample it every 1 second. Again, we're sampling it at the same point in the period, so we're getting a constant. So we should have expected that. And our sketches actually prove that that's true. So the signal we get out, the discrete time signal, is 6 cosine pi over 4, which again is a constant. So this is a constant. And when we reconstruct, we get that same constant signal back. So this was a slightly boring case, I guess. Once we had done case 3, we could almost directly do case 4. So we've looked at 4 different cases of sampling, and this illustrates a broad range of what we get when we sample sinusoids. So hopefully you found this useful, and if you can do these type of sketches, you can pretty much solve any problem with sampling with sinusoids. Okay, so that's all for this video, and it was made for the ECE 201 course in fall 2014. If you want more information about George Mason University or our ECE department, check out these websites. Thanks for watching.